We are going to begin our discussion of chapter 16.3 today with some more conceptual ideas. We're going to talk about two very related concepts. The first one being path independence and how that relates to a specific type of vector field that we call conservative vector fields. So conservative vector fields they're just a type of vector field, or it's a very specific type. And we will discuss why they're so critical and why they're going to be helpful in the future. So let's start off with a couple definitions, and we'll walk through what each of these mean. So this first definition is, let the vector field F be a vector field on any region in space. So this could be 2-dimensional, 3-dimensional, 4-dimensional. And suppose that for any 2 points, A and B in that region, the line integral along some curve from A to B is the same, right? So it evaluates to be the same over all paths from A to B. So what this means is that the path you take, C, as long as the beginning and end points are the same, the evaluation of this integral doesn't matter. So then that means that this integral is path independent, right? So let's draw a little picture of what the heck this is saying. So this is saying that I'm going to take D, right, this region D in space, to be a 2-dimensional plane, right? So we're just going to draw the 2-dimensional version of this idea. So if we have, let me draw some better axes. So if we have like this and this, right? So here's X. And then let me draw just a random vector field F. So F is going to be this, these vectors in red. So maybe maybe it's this one we've seen quite a bit, where the vectors are all pointing straight out from the origin, right? We've seen this one a couple times. All right, so this is the vector field we're integrating through. Looks kind of like this. I'm just doing this as an example. Okay, so here's F. And now let me get a little bit thicker marker to do C. So now we're going to draw a random path C from A to B, right? So let's say here's A and here's B. So our two endpoints of our path that we're going to integrate across. And maybe here's, maybe the first C we try is just a straight line. Right, so here's C1. Right, so we could evaluate that integral. So maybe the integral from A to B on C1 over this vector field dot dr, that's going to be the exact same as any other path, as long as the endpoints are the same. So maybe I'll pick C2 to be this guy. Maybe we take kind of like a half moon shape. All right, so maybe this is C2. So that's going to be the exact same integral as the line integral along C2 of this vector field, right? And we can pick any other path. So maybe we'll do one that, comes over here and does that. Maybe that's a third path we could take that joins the points A and B, right? So the evaluation of the line integral along C3 through that vector field would be exactly the same. So if any path C that we take that joins points A to B, if they all give the exact same evaluation of the line integral, then we know that this line integral is path independent, because it does not matter what path we take, whether it be a straight line that connects A and B or any other path we can imagine. All of them are going to be the same. And what this tells us is that the line integral is path independent, but it also tells us something special about the vector field, right? So the property of the vector field is that it is conservative. So if all paths, let me write this out. So if all paths give same line integral, then the vector field is conservative. Right, so a conservative vector field is path independent, which means that if you know you have a conservative vector field, then it does not matter the path you take to integrate through that specific vector field. And we're going to look at how you can tell if a vector field is conservative and some of the other ideas that come along with that here on the next page. But let's get another definition out of the way real quick. So if a vector field is defined this way, right? So this vector field is the gradient of some other function, right? This function little f, then that little f function is called the potential function for the vector field, right? So this recalls back to an idea we had 2 sections ago, that the big idea we proposed there was that gradients of functions are vector fields. Gradients of functions are vector fields. Right, but not every vector field is a gradient of some other function, right? But not every vector field is a gradient of some, like little f, right? So we take the gradient of little f to get the vector field big F. And so if we know big F is the gradient of some function, that function, right, this function here that you take the gradient to get big F, right, then that function you gradient is the potential function that's called the potential function of big F, right? So if we have some vector field and we know it's the gradient of something, that something that you take the gradient of is the potential function, right? So the way we could write that out is like this, right? So we know that the gradient of this is equal to a vector field, where this is, let me get some labels on here. So this guy, that guy is the potential function. And this guy is a conservative vector field. Right, so the idea is that if your vector field is the gradient of some potential function, then the vector field must be conservative. Right, so that is how we get conservative vector fields. So that's a really big idea as well. So if your vector field is the gradient of some potential function, then your vector field is conservative. So that is the definition of conservative vector fields. So conservative vector fields are the gradients of potential functions. And And so that leads us really nicely into the fundamental theorem of line integrals. And so the fundamental theorem of line integrals is saying that if you have a line integral through a conservative vector field, right? So this has to be conservative. Then the line integral is just equal to the difference between the potential function evaluated at the end and beginning points. So this little f is the potential function. Potential function of your vector field evaluated at the beginning and end. And this looks very similar to the fundamental theorem of calculus from Calculus 1. So let me draw a little comparison here. So from Calc 1, right, we knew that the fundamental theorem of calculus, right, as we knew it before, was the integral from a to b, and we can write it like this, of the derivative of some function was equal to, right, the integral of that function, which the integral of f prime is just f, evaluated at the endpoint minus f evaluated at the starting point, right? And so you can see that this formula here from Calc 1 looks kind of similar to the fundamental theorem of line integrals. If I rewrite it this way, right, so let me rewrite f to be the gradient of something. So that would be the line integral of the gradient of some potential function dot dr is equal to that potential function evaluated at the endpoint minus the potential function evaluated at the starting point. Right, so this looks a little bit more close to this. If you think of the gradient as being kind of like the multivariable version of the derivative, right? Because it's the derivative in every direction attached to a component, right? So it's the integral of the derivative is just equal to the difference of the function at the endpoints. Same thing here. The gradient of a function, the integral of the gradient of the function, is equal to the difference of the function evaluated at the beginning and endpoints. And this is true, right? We can use this because if our function is a conservative vector field, then we know it's path independent. That's what we discovered up here, right? So conservative vector fields are path independent, so it doesn't matter what the curve C is. All we need to worry about is the difference between the starting and end points, right? Let me write that out. So because f is conservative and path independent, those go together, independent, we just need to evaluate at the endpoints. Right, so it doesn't matter what our path C is, we just need to evaluate at the endpoints. Right, so if we're given a conservative vector field, we can ungradient it, right, so undo the gradient to find that potential function, and then just evaluate the potential function at the endpoint minus the potential function at the beginning point. And so this is the multivariable version of the fundamental theorem of calculus, right? Let me just box this. Right, so that is kind of like our Calculus 3 version of that formula. Let's do a couple more definitions. This section is not going to have a whole lot of practice problems. I really just want to go through and iterate all of these definitions and what these ideas means. So we've said this multiple times. So conservative vector fields, right, they are the gradients of potential functions. So we've said this multiple times now. That is to say, that the gradient of a potential function is equal to a vector field where this one must be conservative. Right, so if it's the gradient of a potential function, or just any function, then it is a conservative vector field. And how do we test that? So how do we know? This is the next question we have to answer. Let me pick a color to go with. Yeah, so the test. This is, how the heck do we know whether our vector field is conservative or not? So how do we know? How do we know by just given f if it is conservative? So we have something called the component test. So we use the component test. And this is what the component test looks like. Let your vector field be mi plus nj plus pk. Let me write that a little nicer. Pk. So if this is just our generic vector field and we want to test whether or not it's conservative, so that's what this is saying, then these inequalities must be true. The partial derivative of p, so if this is true, if the partial derivative of p with respect to y is equal to the partial derivative of n with respect to z, and the partial of m with respect to y, with respect to z, is equal to the partial of p with respect to x, and the partial of n with respect to x is equal to the partial of m with respect to y. If all of these are true, if all of these inequalities are true, this one, and this one, then we know it is a conservative vector field. Now, if you just have a two-component vector field, which is an I and a j component, then you only need to test this last one, because it will only have m and n components. There won't be a p, so you can't do these two equalities. So this test right here, all three of these must be true for a three-component vector field. But if your vector field only has two components, then we just do this. So if f is equal to just mi plus nj, then this is our test. So our test is just this last one. Right? But if it is a three-component, then we have to have all three of those inequalities equal to each other. So if all three are equal, it is a conservative vector field. So if all three equalities are equal, then we know f is conservative. How do I get rid of that? Okay, cool. Oops. So that's the component test. And then the last idea I want to talk about is a special property of conservative vector fields called the loop property. So the loop property, this applies to conservative vector fields. And the loop property, let me just state it right here. So remember that this notation, right, that implies that the path we're integrating forms a simple closed loop. Right, so the loop property states that if f is a conservative vector field, and if C is a simple, actually it's just a closed loop. Then every line integral evaluates to 0. So then the line integral of f over the path C is 0. And let's write that out in like mathematical terms. So the mathematical notation for that would be that the line integral, let me do it a little bit bigger, so the line integral over a closed curve C, so it forms a loop, of a conservative vector field will always be 0. And that's true because if you remember from up here, if we're on a conservative vector field, remember it's path independent. So take, for example, if I have a closed curve, maybe like this, right, where that point is both A and B, right? It's the starting and end point is the same because it forms a closed loop. Then when I evaluate, using that fundamental theorem of line integrals, if A and B are the same, right, then the difference is going to be 0. Because if A and B are the same, this could be rewritten as f of A minus f of A, because A and B are one and the same. So this will always evaluate to be 0. So any closed path over a conservative vector field will give you 0. So if C is a closed loop, then the line integral of that vector field over that closed loop C will always be 0. And that's what this is stating here. And that's because, right, this from A to B dot dr, right, that's going to be equal to f of A minus f of B, right, where that's the potential function of the vector field. But we know that if A is equal to B, right, that is to say it forms a loop where the beginning and end points are the same, then we just get f of A minus f of A, right? Because A and B are the same, which will always be 0. That's why that works. So we just covered a lot of conceptual stuff. So I want to make a little bit of a review here at the bottom. That just kind of reviews all of these ideas. So here's just going to be a review. So a review of ideas. So we'll start with finding or what conservative vector fields are. So 1, if a vector field is a potential function, it's not a potential function. So if a vector field is a gradient of some other function, then it's conservative. That's the definition of conservative vector fields. And in this case, we call that function we take the gradient of the potential function. Potential. The potential function of f. So this would be written as the gradient of the potential function is equal to a conservative vector field. So that is the definition. And so if f is the gradient, it is conservative, and in that case, it would imply, right, that if f is conservative, so if f is conservative, then we can then it's path independent. Right? And so that means any path through a conservative vector field will give you the exact same answer. So from A to B, it could be this path, it could be this path, it could be this path. They will all be the same, not necessarily zero, but they will all be the exact same. So that's what this idea was saying. And then we talked about the fundamental theorem of line integrals. So if f is conservative, then we can apply that fundamental theorem of line integrals, which was saying that the line integral over some path of a conservative vector field is just equal to the difference in the potential function evaluated at the endpoints. So this is the fundamental theorem. The fundamental theorem of line integrals. So we can use the potential function to evaluate. So that's what that idea was saying. Then we discussed the test. So we discussed that you could test. We can test f for conservative using that component test. That was up here, where if it was a 3-component vector field, we would have all 3 of these inequalities be equal. But if it was just a 2-component vector field, only this last one, right? We only needed to satisfy this last equality. And the last idea we talked about was the loop property. And that was because it's path independent. On conservative vector fields, they're path independent. Then if the starting and end points are the same, it will always be 0. This is actually number 5. So that means for a conservative vector field, all closed loop line integrals evaluate to 0. And that's what we talked about here, right? Because the starting and end points will be the same. So this fundamental theorem of line integrals states that it will always evaluate to 0. This is kind of the best overview I could give of all the conceptual ideas we talked about that are going to be useful for knowing as we progress through chapter 16. So all of these ideas are related. The conservativeness of a vector field means it has a potential function. If it is conservative, then it is path independent. And because it's path independent, we can use that fundamental theorem of line integrals to evaluate a line integral by just finding the difference in the potential function evaluated at the endpoints. And then the other 2 ideas that went along with that were if we're just given a vector field and we want to know whether or not it is conservative, so we can apply all of this stuff, we just use the component test. And anytime we know that we have a conservative vector field, maybe we did the component test and found out that yes, it is conservative, and we see that the path of integration forms a closed loop, then we don't need to evaluate anything, we know it will be 0. So these are all the ideas that go with conservative vector fields and path independence.